Now, our next set of problems rely on us doing some techniques that we're going to talk about, but they're not too bad. It just requires some manipulation. What we want to do is be given a polynomial equation and then be told to find a new polynomial equation depending on what we're going to do with the roots. So we can do this in a number of ways, and the 4 ways we can do it here. If we're given a polynomial equation and the roots are alpha, beta, and gamma, so it's going to be a cubic, obviously. We want to find the polynomial equation where the new roots could be some number multiplying by all 3. Or it could be some number added to all 3. Or it could be the reciprocal of all 3. And the one that gets asked a lot, because there's the most manipulation, is where we take the square of all 3 roots there. And what we're going to do is create a new polynomial equation. So there's a number of ways to do it. I'm going to try and go through the most efficient way I know to do it. And what it requires us to do is to take the existing equation we've got and then replace the roots in the equation. So if we're given this situation, what we're going to do is replace x in that equation. So if it's k times alpha or beta and gamma, we're going to replace it by y and k. If it's plus k, we're going to substitute it with y minus k. If it's 1 on alpha, 1 on beta, 1 on gamma, we're going to replace it with 1 on y. And if it's square of all those, we're going to replace it with the square root of y. So what we're hopefully noticing here is that when we do this, we want to replace it with all the inverse functions. So the replacement variables will be inverse functions there. So when we talk about inverse functions, what we're looking at is the idea that they are curves that are reflecting. So the inverse of y is equal to x plus 2 would be y is equal to x minus 2. So see how it's because we've swapped the x and y's over. And something for an exponential curve would be a log function. We've talked about that before because we see a reflection of that in e to the x. Now the one that looks a bit strange out of all of them is y is equal to, when we've got to replace it by 1 on alpha and 1 on beta and gamma, where why do we just take the same thing? Well, if you have a look at y is equal to 1 on x, so the graph of the equation here, if we reflect it in the line y is equal to x, then we see that we get exactly the same. So the y is equal to 1 on x is the inverse function of y is equal to 1 on x. So that's why we get that there. So let's have a look at how we do it. I've included that in your notes for you to have a look. That's just an explanation. That actually comes from the Arnold book. It's not a bad explanation of what we're going to do, but really I'm going to explain it to you as we go through and do the question. So basically that's going to say that do the same thing as what I'm getting you to do. So let's have a look. We've got PQR are the roots of the equation x cubed minus 4x minus 7. So write down the cubic equation in x whose roots are p cubed, p squared, q squared and r squared. So as we said in our table, because the roots are going to be squared, we want to replace it with the square root, with the inverse function. So let x be equal to the square root of y. So I'm going to have that situation. X cubed becomes y to the power of 3, and that's why y to the power of a half, all the power of 3, or y to the power of 3 on 2, and 4 times y to the power of a half. I'm going to take them 7 across. Now what I'm doing is I want to manipulate this. Sorry about that. We'll just cancel that and move it back. What I want to do is manipulate this so we can basically want to get rid of the squares. It should be a cubic equation. We want to write down the cubic equation there. So what we want to do is end with something like that. That's what we want to actually end up expanding something like that to get x and x. So it should be an x cubed. So what I do is manipulate it this way, and it's just a little trick you need to realize. Factorize y is equal to half. I can't just expand that out because if I square that side and square that, I'm going to get something a little bit nasty. But it's a little bit nicer if I take out the y is equal to a half, and that leaves us with y to the power of a half outside of y minus 4 equals minus 7, and then square both sides. So I get the y to the power of 1, y minus 4 all squared, and minus 7 gives us a 49. Now, given that situation, I can expand that out. So that's y squared minus 8y plus 16 multiplied by the y gives us the left hand side here equals 49, and then our cubic. Now notice here I've got it in terms of y and I've put it back in terms of x. It doesn't really matter what variable you put it in. So you could put it in z, you could put smiley faces in there if you like. It really is just a pronumeral. It doesn't matter whether it's a y or an x or a z or a smiley face or anything else. It's just a polynomial in turn, which is a cubic. But it said write down the cubic in x. So I've returned it to x as we've got in the start. If you left it in that form in y's, wouldn't be a problem. And I've probably throughout these questions I've done that at times. So question 2, again, this is one where it takes the most manipulation, where we've got the x squared, b squared, alpha squared, beta squared, and gamma squared. So again, we're going to let it equal the inverse function, so we substitute square root of y in for x in all those. So, and then we're going to do manipulation. This is a little bit harder because what we want to do is take that term and put it across to the right hand side with the 1 and get that term, because we're going to factorize y to the power of a half out of those two terms here. So, and we're left with the y minus 5 because it's just y to the power of 1, and we're left with the 5 there. When I've got it in that form, I can now square both sides. So I square the y. The power of a half gives us y to the power of 1. Y minus 5 all squared. And then I can square this side. Don't really want to square the whole thing there. I'm going to end up with the ugly things coming up. But if I manipulate and get these on this side, it starts to manipulate very nicely to what we want. So expand your quadratics there, and then multiply by the y on this side. We've got the function on this side, and then we start to collect them on the other, on both sides, so we get our cubic equation. It should be, if we've got 3 roots, we should get a cubic. We know that 3 roots gives us a cubic, 4 roots would give us a quartic. So let's have a look at this one. We want to write down an equation with the roots of this equation are alpha, beta, gamma. What equation has alpha on 2, beta on 2, and gamma on 2? So again, do the opposite. X is equal to 2y because it's alpha on 2, so we multiply y by 2 and then substitute it in. So 2y goes in there, 2y goes in there, and then expand it out. There's our cubic, sorry. There's our function. This time, alpha, beta, gamma are the roots of this equation, and form a cubic whose roots are that one. So let's have, again, because it's alpha minus 2, beta minus 2, gamma minus 2, let x be y plus 2. So we get that expansion out, and so we need to just expand those terms. It comes down to a very nice little one of y cubed minus 27, which can factorize there. So that's very nice. Lots of terms cleared out and gave us that. Then, hence or otherwise, solve this equation. X cubed minus x squared plus 12x minus 35 over the complex field. So that's why we started to manipulate it and then start to get our factorization. So we were quite happy to form the cubic equation there, but then we need to keep going along because we got y is equal to 3, use the quadratic formula for the square there, and there's our quadratic there. Now notice that the quadratic we've got here is y cubed minus 27. So, and that's where we have the roots of alpha minus 2, beta minus 2, and gamma minus 2. So this is a quadratic that has alpha minus 2, beta minus 2, and gamma minus 2. Now the problem is that we want the original one which have those roots. But if we look at, we know the relationship between this quadratic, this cubic, and this cubic was that we had only the roots differing by 2. What we go back and do, well, if the roots for this equation were y is equal to 3, y is equal to that one. So what we're going to do is add 2 to each side, because if alpha minus 2 is equal to 3, then alpha would be 5, so x would be equal to 5. And if our roots were beta minus 2 is equal to the half plus 3 root 3 on 2. Sorry, b minus 2 is minus root 3 on 2 plus beta would be half because we've just added 2. And we're saying with this one, we've added 2 to get the half there. So there's our roots of the original equation, given what we do there. So let's have a look again at the manipulation we've done, and then we've just got the roots of this equation and added 2 to all 3 of them. This time, back to an equation where we've got the roots of that equation, alpha, beta, gamma, find the square. So again, we've done the manipulation, put x is equal to square root of y, substitute it in, take our terms across, and then we can factorize and square both sides. Expand it out and collect our terms in y, and then we put it back in terms of x again. Doesn't really matter if we leave it in y or in x. So again, cubic equation, find the terms where x squared, beta squared, alpha squared, beta squared, gamma squared. So again, we do that manipulation, let x be equal to the square root of y, put it in, take our terms across on both, and so we got terms on both sides, factorize here for this term and this term, the y power of a half out, and then square both sides, so we get expand our to our quadratics there, and then collect all our terms. So there's part 1. Then we want to find the value of alpha squared, beta squared, alpha squared, gamma squared, and beta squared, gamma squared. So if we have a look at what we do there, we can just, that's really just the roots 2 at a time of our new quadratic, of our new cubic. So we just want the roots 2 at a time of that one, which would be the minus 12 on 1, which gives us 12. Not too bad if we know, if we get the first part. It works out easy. So in question 7 here, this time we've got a graph and we want to, we can see we've got 3 points where they intersect, which means if we solve these 2, we would have 3 values. So let them be alpha, beta, and gamma. So we'd have 3 roots. So we're going to want to find alpha, show that they're the roots of that equation. Well, if we get the equation there, make them equal, solve them simultaneously, multiply through by x and collect our terms, well, that's going to be our equation. That's not too bad to do. And then we want to find the polynomial, which has the roots of alpha squared, beta squared, and gamma squared. Again, do our substitution, let x equal the square root of y, do our manipulation. So it's not a bad little manipulation this time. It's pretty easy. All we've got to do is take the 1 across, factorize the y to the power of a half out, and then square both sides, and then collect all our terms, expand it out, and collect the terms on the left-hand side. So that's how we do those ones. Have a look through. Make sure you understand the process. If you're not sure, then you've got to ask some questions because this is the one. As you can see with the questions I've asked, these are ones that are going to pop up a lot. Because that's the one. This is the situation out of all 3 that takes the most out of all 4 that takes the most manipulation. The other ones, not so much. This one requires on this nice little technique to work through and manipulate the algebra around to get our new cubic equation. So we've got to know how to do that process.